It's a great pleasure to be here. I'm really enjoying talking to people and learning a lot about what everyone's doing. Yesterday I talked about structured population models and growth rates for structured population models, and looked at, say, the eigenvalue for a matrix and what that tells us, and the net reproductive rate. And then we talked about how to use this kind of interesting graph theory method to calculate R0. And then we saw that we could actually use this to understand things like the growth of a weed species. Today I want to talk about another direction. And I'm going to relate these two directions at the end of my talk. And I think, philosophically speaking, these two lectures are tied together somehow. And one of the things is, when we look at invasive species, things get very, very complicated. And there's a lot of uncertainty. And so often exact numerical simulations of complicated outcomes are very interesting, but they may not be able to predict things very well, because there are a lot of uncertainties. And there are a variety of ways of dealing with this. One is to run a lot of simulations and look at the spread like we do for climate change. The other that is useful for invasive species is to come up with a single number that encapsulates essential ingredients, and then use maybe just a single number to describe the invasiveness of a plant. And this single number could be the growth rate if you're interested in how quickly it's growing locally. But this single number could be the spreading speed, or the rate at which it moves into new environment, if you're interested in how quickly it moves through this sort of second stage of once it's established, spreading into new regions. And even though the details of the models underlying the calculation of a single number are quite complex, at the end of the day, you have this number, and then you look at ways maybe you can reduce it by strategies for control. And so in this case, the number we'll be thinking about, the quantity we're interested in, is the slope of a line. And we saw this picture very nicely the other day in Jasek's, I think it was his talk, and Yuri's talk, sorry. My apologies, Yuri. This was, there was this release of muskrat near Prague in around 1905, and these were initially farmed, and then they got out and they reproduced and they spread spatially, and there's some kind of map of how they spread across Europe, and it has a sort of target pattern, very interesting, goes back to the 1950s. This very influential biologist called Skellum wanted to know how quickly invasive species spread, and he plotted something like the square root of the area versus time, and the slope is pretty much constant, except it's a little different during the First World War, which is kind of interesting. The slope of this line we can think of as a speed. It's got units distance over time. And this is describing how quickly it's moving into this new environment and occupying new territory. And so if you're concerned about an invasive species, this is a really important quantity to consider. If you actually look back in history, this idea of spread has been around for a long time. And Fisher was a geneticist, and the same Fisher that you might know from statistics. He was interested in the rate of change of density of an advantageous gene in his context. And there's a growth term, which we think of as logistic growth. And then there's dispersal, which we can describe via diffusion. And so this is a partial differential equation. And we add this random motion, or diffusion, to logistic growth. And he thought about this in terms of the rate of spread of a gene into a new environment. We can think about this in terms of the growth of a population and its spread. And here the carrying capacity for the population is essentially 1, okay, the way it's written down. And this is like really the most fundamental equation for the spread of an invasive species. So we think of the growth as this nonlinear function. And it's actually quite useful to look at the units for the coefficients r and d. So r is some kind of growth rate, okay? And it's got units 1 over time. And d is a diffusion coefficient, and its units are space squared over time. So it's something like mean squared displacement per unit time. And f is this kind of sad face. This is what I use when I teach calculus, right? A sad face function that's concave down. And so this is the uninvaded state, and this is the invaded state at the carrying capacity. And so if we look back in history, people have been very interested in this model for a very long time. 3 famous Russian mathematicians, Kolmogorov, Petrovsky, and Piskunov, originally analyzed this equation. And what they found was sort of amazing. If you start with an initial population that's invaded over here, okay, and it's uninvaded over here, and then there's some kind of transition in between, that eventually this thing would start spreading at a speed, and that speed was given by c star, which is 2 times the square root of the growth rate times the diffusion coefficient. And that's kind of interesting. If we look back to the previous slide, r has got units 1 over time, d has got units space squared over time. So r times d has got units space squared over time squared. If we take the square root, that's got units space over time. So it's suitable for a velocity or a speed. And they actually calculated that that was what the speed was. And it turns out that actually a chemist called Luther in around the early 1900s was looking at these spatially distributed chemical reactions. And R was a reaction rate, and D was the rate at which these molecules were diffusing around. And he determined that the spread of the chemical reaction was proportional to the square root of R times D, really just using a dimensional analysis. And so looking at dimensions is really quite useful if you haven't done it before, just by looking at what the right units are for the quantity you're interested in. You get a bit of a feeling of what might be possible. Well, it turns out actually, even though the work by these Russian mathematicians was very foundational, if you have an invasive species, normally what you'd see is you'd see some local introduction of that species, and then it would grow and spread. And so those initial conditions that Kolmogorov et al. Were using are not really the correct ones. They might be correct after a long time when all this area is invaded and now it's spreading spatially. But initially, there'd just be this little beachhead, okay, where the species is introduced, and then it would spread spatially. And so this idea was picked up in the 1970s by 2 mathematicians from the University of Minnesota, Aronson and Weinberger. And the little dotted line shows the initial conditions. And so what they showed is that the same population now will spread spatially in both directions, okay, at the same speed, c star. And if you're a mathematician, these papers are very beautiful, right? They're a little bit hard to read, but they're very, very nice papers, very foundational, and they have a lot of methods that are useful for partial differential equations. And so if you're interested in this area, what they did is they created one solution that we call a super solution, and they showed that that would spread at speed c star. And then they created another solution underneath, which they call a subsolution, and they showed that would move at speed c star. And then the true solution would be sandwiched in between. And there's this thing for these kinds of equations called the comparison theorem that says that solutions can't move through each other. And so this would then have to also spread at the same speed. Okay? And so for these kinds of equations, if solutions are initially well-ordered, they stay well-ordered for all time. Okay, and then as I mentioned, Luther argued that the speed of a related chemical reaction was proportional to the square root of r times d. So this is kind of interesting because this kind of goes along with the idea of having a simple statistic that we can use to estimate the spatial invasiveness of an organism. Because if we can calculate the growth rate and the diffusion coefficient for different species, then we can have this number, this magic number, C star, which describes how quickly they're going to spread. And indeed, at the time that I was doing my postdoc, which was actually rather a long time ago, around 1990, ecologists were getting very excited about this theory because they said, hey, we can go out and measure the invasiveness of different organisms from measuring the growth rate and the diffusion coefficient, and then we can compare our theory to actually what's observed. And maybe this can help us understand why some species move very quickly into new environments and why other species move very slowly. It could either be the growth rate or it could be the diffusion coefficient driving these processes. So we'll come back to that. And I'm going to skip through that part. One way we can think about the spreading population is in terms of something called a traveling wave. So a traveling wave has a shape, and it keeps a shape, and it just moves across the domain at a given speed. And so if we start with our initial model, which is shown up at the top there, which is Fisher's equation, then what we do mathematically is we change to traveling wave coordinates. And so instead of thinking of u as a function of space and time, we think of u as a function of this moving coordinate. Now the coordinate is moving at speed c, say to the right, and so u is capital U of z, where z is x minus ct. And that translates the first equation into an ordinary differential equation. We use the chain rule to get du dt is minus c times u prime, and duxx is du double prime. And so what we're doing is looking for a solution that looks like this. This is z here, or z if you're from the United States, or probably most of the rest of the world. As z goes to, or z goes to minus infinity, you go to the carrying capacity, and as it goes to plus infinity, you go to 0. And so this is an ordinary differential equation, and it's given right there. And it turns out when you analyze this ordinary differential equation, it's possible to show that such a solution exists for every c greater than or equal to c star, which is 2 times the square root of r times d. So we say like there's a family of these solutions, okay, and they're going to move at least as fast as c star. Okay, so this is kind of very classical theory, and you might say, well, okay, that's interesting. We've got partial differential equations, ordinary differential equations, but how do we understand this c star? Where does it come from? This 2 times the square root of r times d. And it turns out what we can do is think about what happens at the very leading edge of the wave. And so you're way out at the very front of the wave, okay? There's no density-dependent effects. You're just sort of almost off by yourself, okay? You're the leading invader, and very low densities around you. Okay, so if there's low density, you don't have to worry about crowding from other individuals, and you can just grow and disperse and do your thing. And so the idea is that we would, rather than putting the function f in the equation, we would just replace that with r times u. Okay, so we've replaced a nonlinear function with a linear function. With I better draw it here. So this is f of u, and it looks like this. And this is r times u, and f is r times u times 1 minus u. Okay? So we can write this as being f prime of 0 times u. So this is called linearization. And so if we think about this here, we're close, for u is close to 0. And so if we have this wave that looks like this, we're out here at the leading edge of the wave. Okay, right at the very front, trying to see what's going on. Okay, that's the equation. And the beauty of this equation is it's linear, so we know how to solve this equation. Or if we don't, we can look it up or ask our neighbor. Okay, so if you look it up or ask your neighbor or do it yourself, what you end up doing is you see that this becomes a little bit like in, now I have to remember whose talk this was, if it was Jacek or Yuri. One of the talks yesterday, where we saw this Gaussian. We see the solution to this, if we start with individuals at one location, is a Gaussian, okay, bell-shaped curve, a normal distribution that grows like e to the RT. So e to the RT is scaling the solution, is exponential growth, and then the normal distribution is a bell-shaped curve, and the variance is 2 times d times t. And so this is what's shown here. This is the curve. It's growing up, and it's spreading outwards as the variance gets larger. And it turns out if you take a level set of this curve, say there's some detection threshold here, u sub c, and you call this point x sub c here, and it's the point at the very leading edge of the wave where you can start to detect individuals, then as t goes to infinity, this point will go exactly to this special speed, c star, 2 times the square root of r times d. And so this shows that really the spread of the population is governed by this linear equation, and the nonlinearity isn't so important. Alternatively, we can look at this a different way, and what we do is we say, well, we're going to look for a traveling wave solution now. We know about traveling waves, and so we're going to look for something that looks like this. So it's going to be an exponentially decaying solution. It's going to move at speed c. So it's going to be, is it u is proportional to some constant times e to the minus s x minus ct. So that was the traveling wave coordinate z that we saw before. And this is an exponentially decaying solution here. Okay, so we have this linear equation. And then we put in that traveling wave ansatz and look for a solution that's spreading like that. And so if we put that into the equation, then when we calculate du dt, we're just going to pull down a c times an s. And then we have an r times u. And we calculate uxx, we're going to pull down a s squared. And so when we put this into the equation, we have the following. It's c times s times u is equal to alpha, r times u. R times u plus d times s squared times u. And so this says either u is equal to 0 or c times s is equal to r plus ds squared. So we can think of c of s being r over s plus d times s. Okay, so this is a speed, and the s is a steepness. Of the wave. Okay, because when s is large, it's a steep wave, and when s is small, it's a shallow wave. And so this is what's called a dispersion relation. And the idea of relating the speed of a wave to something about the wave really comes from physics. And the idea there was people would be interested in how quickly waves would move as a function of their wavelength. Here we're interested in how quickly this population spreads as a function of the steepness of the wave. And so if we plot that c function, c is here and s is here, as s gets small, it's going to blow up, okay? And as s gets large, it's going to grow linearly, and there'll be a minimum here. And it turns out that this speed c star, this spreading speed or traveling wave speed, is the minimum that this dispersion relation gets. Okay? So this is a very common way of writing this idea of a spreading speed for a population. It's the minimum of this speed coming from the dispersion relation. And here we have 2 times the square root of r times d. And this is the steepness of the wave that gives us that. So we'll be doing this in the lab for a slightly different formulation. Okay, so we'll come back to that. So we've kind of got 2 ways of looking at things, this way and that way. Yeah?
What's the steepness?
Sorry?
What's the steepness?
Oh, the steepness biologically. Yeah, that's a really good question. So what is the biological interpretation of the steepness of the wave? And so if we think about, yeah. Ah, yeah, thank you. So this is our spreading population. And what we're doing is we're looking at what's happening right at this leading edge here. And this is e to the minus s x minus ct is this solution here. This is x, and this is u. This is u for the linear equation. So this is for the linear equation, and this is for the original equation. And so if we look at s here, s is how quickly the population drops off as you get to the edge of where it's spread to. And so if s is small, you have a shallow wave. And if s is large, you have a steep wave. And so, sorry?
Because how quickly it drops off is actually given by the original f of u.
Well, if we look at the linear equation here, then we're just looking at what's happening at the leading edge of the wave at this part, and we're not worrying about what happens back here. So we're just kind of focusing in on the leading edge and ignoring what's behind. Yeah. So it's how quickly it drops off at very low densities. But there are other factors in play back here. But it turns out for this particular equation, those nonlinearities that happen far behind the wave don't really matter. Okay? Even though they add realism to the model, we get exactly the same speed for a linear model as we do for a an equivalent nonlinear model, which is kind of nice. It's kind of amazing in a way. And in my lecture notes, I have a little section, which I'm not going to go through right now, that talks about when this works and when it doesn't work. So it works for Fisher's equation very nicely. And so I thought we'd kind of focus on that one. Okay. Yeah.
How quickly it drops off, is it equivalent how rapidly it was increasing?
It was rapidly, it was
Increasing.
increasing. Well, if you stood still and the wave swept over you at some speed, c star, if it was a steep wave, you would see it increase locally, quickly, as it swept over you. So if you're standing still and the wave comes by, if it's a steep wave, you'll see the population rising quickly. If it's a shallow wave, when it sweeps over you, it'll rise much more slowly. So it's how quickly it's changing relative to a stationary coordinate.
I have a concern. Going back to the invasion,
Mm-hmm.
for example, rodents. Is it possible to model, to track back? For example, you don't have data of when this introduction was done.
Ah, I see. Yeah.
Yeah.
So you kind of run your equation backwards
So
somehow.
to look at the time back such that in case you have to model the management.
Yeah, that's a really interesting question. So what happens is it's a very hard problem to solve. And the reason is because diffusion ultimately spreads things out and it destroys information. And so if you have something like a heat equation and you run it forwards, you can describe, or diffusion equation, you can describe how things move. But if you run it backwards, you get what's called an ill-posed problem. So somehow you're losing information about the initial beachhead of invasion if you let this progress over time. And so it's a tricky problem to solve. I'm not sure if anyone's done it. I mean, I think my gut feeling is you could do it to a point, but then you wouldn't be able to tell exactly what the initial introduction location was.
Because my assumption is that if you choose in between the time and you run experimental design, you could perhaps cut off the sanity time of monitoring and the video and then you observe to see how it spreads. Then perhaps you could tell when this happened, the introduction was done.
Mm-hmm.
And then
Mm-hmm.
it can help you to do the management in case you're
Yeah, it's very appealing thought. Yeah.
But
Yeah.
I'm not a mathematician.
Yeah. No, this is really interesting. So, yeah. So, my feeling is we should be able to do something like that.
Yes.
And, yeah. So, well, let's talk more about it.
Okay.
I'm not aware of anyone having done this. So, yeah. Okay. Thank you. Yeah. Are there other questions or comments? Okay. All right. So this was, like I said, when I started as a postdoc, this was really exciting for people because they thought, invasions are a real issue, but now we have this theory that's telling us if we want to know how quickly a population spreads, we don't have to have a PhD in mathematics necessarily. We just need to be able to calculate a growth rate and a diffusion coefficient, and then we can look at how quickly a population is going to spread, or its invasiveness, just by calculating the C star. And so some work in the late 80s and early 90s calculated a spread rate theoretically from looking at populations and measuring their growth rates and how quickly they moved. And then they looked at historical record of moving range boundaries, let's say the muskrat moving across North America, or even Black Death spreading from close to Italy up north during medieval times. And they compared observed to theoretical. And that looks pretty good. it helps, it's a log-log scale, okay? Wouldn't look so good on regular axes. But there are some things that are way off the line, okay, like these things here. So somehow this theory, even though it's kind of attractive and easy to formulate, is sometimes underestimating the observed spread, okay? So this is an order of magnitude. These are orders of magnitude higher than what is predicted. So it's quite instructive to learn about this example here, which is this cereal leaf beetle, which is a pest in the United States. And it kind of moves like in a kind of a local diffusive fashion within fields and spreads. And then occasionally it's picked up by the wind, and then it's transported a very long way in the wind, and it drops on another field. And so this is a little bit more like the stratified diffusion that we heard about the other day. There's local spread, but then there's occasionally a very long distance spread. And then there'd be a new beachhead of invasion, and then things would spread there, and then it would happen all over again. And so this is where the theory at this point failed to really describe what was going on. But it's clear what's going on in terms of the biology. The case with oak trees, which we don't really think of as an invasive species, was with respect to historical climate change. And originally, a British biologist called Reed was interested in how quickly oaks were recolonizing Britain after the last ice age around 10,000 years ago, approximately. And he saw historical records showed that they colonized very quickly behind the retreating ice sheets. And he couldn't understand why they would be able to do this so quickly. And we see the same thing in North America if we look at pollen records, say for the oak. And the blue shows the retreating ice cap. And this is pollen for one species of oak. And the levels are shown there. And as the slides progress, we're getting closer to now. So those years are before present. 20,000 years ago, 18,000, 16,000. And so we see this oak population, at least from pollen data, seems to be staying right up with these ice sheets, not lagging behind very much. And so the spreading speed for these populations was around 100 meters per year. Okay? And so this is very rapid, right? And we can understand this from the perspective of climate change, like can a population keep up with climate change? But we can also understand this from the perspective of if we think of the oak as an invader into this new environment that's being opened up by the retreating glaciers, how can it do this so quickly? And Reed was in the late 1800s, but this guy Skellum, who we talked about previously, picked up the challenge. And this is what Reed wrote. The oak, to gain its most present most northerly position in North Britain after being driven out by the cold, probably had to travel fully 600 miles. And this, without external aid, would take something like 1 million years. So you'll notice he was before Fisher and Kolmogorov. Okay, so he didn't really have all the mathematical theory at his disposal. And 1 million years is a little on the long side, I think. But there's an issue there. And so in the 1951, Skellum picked up the mantle of Reed's question and tried to understand what was going on. And at that point, this theory from the mathematicians, Kolmogorov, Piskunov, so on and so forth, and Fisher had been already described. And they knew about the speed here. And so they said, we know how quickly oaks produce acorns and so forth, and their average lifespan, so we can compute an R. And, but we'd like to know about this diffusion coefficient that would have to be in there so as to describe the historical spread. And sort of this is like a back of the envelope calculation. And so what he calculated was that the sort of average dispersal distance for an acorn from an oak tree would have to be 830 meters. Okay? In English, there's this saying that the acorn falls close to the tree, right? It's often used to describe people from their parents, but usually they fall right down, right? They don't go a kilometer away. So this was called Reed's paradox. And it's a kind of an essential paradox. If we're going to use theory and we see that it fails abysmally, we have to find out what's going on somehow. And and this is partly why Skellum was so influential. He really confronted theory with data and then got people to think about things in a new way. Okay, so it turns out that when we look at plants, there's all kinds of similar situations. That there's rapid spread through rare long-distance dispersal events. And sometimes this even leads to waves that are accelerating. And we saw this in yesterday's lecture, it was mentioned. And so there isn't even a speed C star. These waves start off slow and then they go faster and faster and faster and faster, as that's what the historical record shows. And so instead of having a straight line of distance versus time, this is time, this is distance. This is what the theory would predict, but often we see things that look like this, okay? So this, the slope of this is C star, but here the slope is changing over time. So we need theory to understand that. And one of the theoretical constructs is this idea of stratified diffusion. And we heard that mentioned. Another is to try to find a way to put realistic dispersal functions in models. And the beautiful thing is we can measure dispersal data for lots of different species. And so we should be able to use this in our models and not just put in diffusion. Diffusion is a rather crude depiction of what's truly going on. For example, if there are some rare long-distance dispersal events, then they would show up in a dispersal function. And so here, a dispersal function would describe how far propagules go over a season, like typically a year, when there's a periodic reproduction. And so for any species, often people collect data with things like seed traps and so forth.
Sorry, Mark.
Yeah.
On that data, is there a time scale involved here?
Yeah, so yeah, so this is over a single season, or essentially a year, a dispersal season. And so rather than thinking about things in continuous time, we're going to actually end up shifting to a discrete time formalism, and where there's, say, yearly reproduction, and then there's dispersal for a fixed amount of time. And so in this case, this is like, say, dispersal of seeds. I think this was elm seeds over a year. Okay, so it's where did the seed land relative to where it started. And so in actual fact, this is a slightly better way of formulating things when we look at discrete time, because a lot of invaders have this seasonal reproduction and then dispersal, as opposed to reproduction and dispersal happening all the time. And so there is a time scale here. It's essentially a year.
What I just wondered was whether the distribution was dependent on time, whether seasonality came into it. Because there's no time in this, it's just the frequency and the distance.
Yeah, that's right. So this is the relative distribution of new wasp nests relative to the original one, when the wasps are creating new nests. And so we have to bring time in at some point in our model, but we're going to end off moving to discrete time. And this is where we build the tie-in to our lecture last day, where we're doing things in discrete time. So we've kind of started with a historical story of how people have thought about things. And now we're about in 1980 or so in terms of time, right? And we have 10 minutes, so so we'll see how far we get, okay? But if I don't get through all the slides, they'll be available. There's a lab tomorrow, and on the lab I've put all the PDFs of these talks, and so everyone should have that on their desktop tomorrow. And you feel free to, sorry? Thursday, yeah. So feel free to keep those slides and do whatever you want with them if you want to read them. Okay, so the idea here is that maybe 99% of individuals disperse locally, and maybe 1% or so of individuals disperse a long way. And these are the cereal leaf beetles that are getting picked up by the wind, or in England, they're the acorns that are being moved by squirrels, okay, maybe 100 meters. And in North America, it's probably jays that are moving acorns and seeds and causing a few individuals to move a long distance. And so this is a long distance dispersal function, and 1 minus p is the probability of moving that long distance. So we can create a composite dispersal function that has local and long distance components. And now we need to think of a way to put this in our model. This is a challenge, right? Because if we have growth and diffusion, things are kind of simple. But now we have this really kind of realistic but complicated dispersal function. And one way that people have used that's been very successful is these so-called integrodifference equations. And they go back to that lecture on Monday where we were looking at a discrete time growth process. Okay, the population at one time step is a function of where it was at the last time step. And so n here is an index for time, and f is a nonlinear growth function. And it's shown in the top right-hand side. And for example, that would be something like the Beverton-Holt function that we saw from lecture on Monday. But rather than just letting things grow in discrete time, we say, okay, first you grow, then you disperse. And this dispersal is with this function k. And so that's where the dispersal kernel comes in. And if you grow at y, you then disperse to x. Okay, so you're moving and jumping to x, and then you're over here, then you grow, and then you disperse again. And so this has turned out to be a very nice way to understand invasions, because we can put in these very realistic dispersal kernels, which can be, say, generated from data or other ways. And so what would we do with this? Well, we could try the same trick that we tried before for the PDE. This is sort of what you do in applied math. It worked last time, so let's try it again here, see if the same method works. And what did we do? Let's just skip ahead for a second. What we did was we linearized the equation. We put in that exponentially decaying wave, and then we got this dispersion relation between the speed and the steepness. And then the speed was the minimum of that, which turned out to be 2 times the square root of r times d. So we can do the same thing here. And so we linearize. So instead of using our full function f, we use lambda times u, which is the growth rate. Lambda is the geometric growth rate at the leading edge. And then that nonlinear function is replaced by a lambda times u, and we have a linear equation. Okay, and then we do exactly the same thing as we did before. We look for a solution that is exponentially decaying, and we plug that into that equation. And then there's some calculations which I don't want to go through. Just trust me, okay? It's a couple of lines on a piece of paper, but I'm sure to do them wrong on the board. And what we end off with is this dispersion relation between the speed and the steepness. And rather than being a nice function like we could write down before, it involves the log of lambda times m of s. And m of s turns out to be this thing here. And this is called the moment generating function of the dispersal kernel. And so we can think of it as a transform. It's almost like a Laplace transform if there was a minus sign in there. Anyhow, so this is what we have, and then this is the formula. And so this was written in a paper in 1982 by Hans Weinberger in Siam Journal on Mathematical Analysis. And it was a very, very difficult to read paper. And no one used the formula. And then I was working with Mark Codd and Pauline van den Driesch on the same problem. And we came up with the same formula. And then we tried to publish it, and it went to Hans for a review. And he said, we had no idea he'd done this work before. He's very, very nice. He goes, it's very nice of you to popularize my method. Thank you. and so he was very gracious about it. And we, of course, referenced his work. And it turned out he'd done it 14 years before. And he'd done it much more rigorously than we had. We were just doing sort of heuristics. He'd done a very deep and wonderful and beautiful proof about some of the issues associated with the speed. And we published our paper in Ecology, and it's become a very popular paper. And so essentially what we do is explain his work to ecologists. And so it really led to an interest or regrowth in trying to understand these things. And it also led to a lifelong collaboration with Hans. So basically about 10 years later, I said to him, you know, I've read your paper about 10 times, and I don't really understand parts of it. And can I come and visit you on sabbatical? And so then this turned into a very productive sort of 10 or 15 years of collaborative work where we extended this theory much further. Okay, yeah. Time? Okay, 2 minutes? Yeah. Okay, so the idea here is that if we look at a population, we fit a dispersal function to it, then depending on the dispersal function, if we capture the long-distance dispersal effectively or not, we see spread at very different speeds. And so at the top, there's a wave that goes to distance 1. This is distance 3, this is distance 20, and this is distance 2. And this is an accelerating wave, okay? And these are waves that move at constant speed. And so the devil's in the details of these dispersal kernels that you have to get their details very well at the leading edge. Okay. So you'd be amazed how much I thought I was going to show you. But I would encourage you to read the last few slides because we'll be doing something on them in the lab. And let's just talk about the summary. Population spread is a spatial measure of invasiveness, much like lambda is a population growth rate that can describe invasiveness. And we can understand the Fisher model. This misses an element of long-distance dispersal, which is crucial. And this is a scientific problem because we can even create models to include long-distance dispersal, but then it's very difficult to measure. And so there's a great deal of uncertainty with estimating spreading speeds because of our lack of ability to measure long-distance dispersal. And say when you look at historical records and you look at beech trees invading North America, well, it could be like a 1 in 100-year storm, the kind that picks up cows and houses and moves them to the next county that is driving these dispersal events, these sort of extreme events that then give the tails to the dispersal kernels. And these are the things we don't usually put in our models. And we can include age or stage structure in these models. And so the last little bit of the lecture focuses on going back to our matrix model from the first lecture and adding space to that. And that's what we'll be doing in the lab. Okay, thank you.
Are there questions, comments?
So it seems what's crucial to all of this is these dispersal kernels.
Yeah.
And linking back to the title of this workshop, I was just wondering whether you can use the dispersal kernels to even track climate change, get some sort of correlation between how dispersal kernels for, say, oak have changed over time, and whether you can correlate that to climate change in any way.
Yeah, so that's a very interesting question.
Can you repeat the question so we can hear it?
Yeah, sure. Did you want to repeat it? Or? I'm happy to, yeah. So, yeah. I think the main thing was that dispersal kernels are key to our understanding. And can we look at historical record of paleo data or something to see how dispersal kernels have changed over time in response to environmental change?
Right.
Is that basically it? Yeah. So what people have done so far is try to look at paleo records to reconstruct spreading speeds, and then use modern day analysis of seed trap data and so forth to try to reconstruct what the dispersal kernel could be. But I think what you're suggesting is going further and actually seeing if from paleo record we could sort of infer what dispersal kernels were.
Yeah.
And yeah, I think that's possible. And I don't really think it's been done very much. So that would be very interesting.
Mark?
Yeah.
First, following on from that, propagule pressure is a huge issue in invasion biology. So how many propagules are added to an ecosystem?
Mm-hmm.
And one of the inferences of propagule pressure is the more propagules you add to a system, the more likely you are to have long distance dispersal.
Yeah.
And propagule pressure is now sort of thought of as you have to use it as a null model to explain why certain species are more or less invasive than others. So I think there's a lot of opportunity to play around with this sort of thing.
Yeah, that's very interesting. And so just to restate the comment, I think, was that propagule pressure is understood as one of the main drivers for invasion success. And it would be interesting to connect this stuff or look at connections. And absolutely, that's a great point. I think that propagule pressure, as far as I understand it, so far has been focusing on whether the initial invasion is successful. But I think you're saying also there's another thing. If you have more propagules, you have a higher chance of a very rare long-distance dispersal event. And that could drive the spreading speed.
So if I could just add on to that briefly, I think there's a lot of interest in understanding propagule pressure more than the initial stimulus for invasion, but the driver for ongoing spread and the patterns.
Very interesting. Yeah, thank you. Yeah. Sorry?
Like, you talked about changing the density.
Yeah.
And you said it's growth plus dispersal. But in the talk, you didn't talk about growth. How do you model growth?
Yeah. Okay. Good question. So how are we modeling growth here? Yeah. Okay. So there were really two models, and the first model for growth was the one of logistic growth. And there'd be something like this. dn dt is r times n times 1 minus n. That would be logistic. And that would be describing a population with a carrying capacity. We could put a k in there if we want. And it would look like this. Okay. And then putting space into that model is Fisher's equation, which is du dt is ru 1 minus u plus d squared u dx squared. So this is diffusion now, plus the original growth. That would be logistic growth. And so this is like a spatial version of this model here. The second way was to look at things in discrete time. And so here we have n at t plus 1 is equal to f of n at t. And here, this could be something like the Beverton-Holt model that we saw the other day. That looks something like this. And now this is the carrying capacity here. And then if we turn this into a spatial model, we'd have u at t plus 1 at x is going to be the integral k of x minus y f of u t of y dy. So this would be growth here, and then this is dispersal. So each of these has growth as a kind of a building block that then the dispersal is added onto. But when I described it, I don't think I talked very much about the growth part. So I'm glad to have the chance to clarify it.
Okay, so maybe I will ask one last
sure.
question.
Yeah.
Just because what you described is essentially it's Levy process and then passage to the deterministic description, it's, and also you can model this using like super diffusion.
Mm-hmm.
Has any work been done in this direction?
Yeah, so you're,
Because essentially, I
the
mean,
dispersal part is could be
dispersal.
a Levy
Jump
process.
is a Levy process, yes. And
Yeah.
there is quite a lot
Yeah.
of modeling now using sort of like anomalous
Yeah.
diffusions
Yeah.
here,
Yeah.
not necessarily going to integral
Yeah.
differential equations, difference equations. So
That's right. So there has been a lot of work connecting the dispersal kernel to Levy processes and so
because
forth.
this
Yeah.
is essentially how we model.
Yeah. Yeah.
But there's also actually a way of looking at this as through anomalous super subdiffusion.
Mm-hmm.
And then
Yeah.
anything was
Yeah.
done in ecology with.
Yeah. Well, I mean, people often think about this as a Levy process with a variable stopping time.
No.
So you don't stop at a fixed time, but it's variable somehow. But then I'm not so much aware of how people have put the growth into the Levy process. So that's another, this is where people often will switch to the deterministic model. But I'm sure there's room for interesting work there. Yeah.
Okay.
Yeah. Thank you very much.
Thanks.
Okay.
Thank you
All
very
right.
much.
Okay.